All right. Good morning, everybody. My name is PJ. I go by as Splenic on Twitter, so if you want to tweet at me, there's a whole great story behind my Twitter name, but that's a whole 30-minute presentation unto itself, so we're not going to worry about that. I work at a company called devrelate.io. We do developer and community relations as a service. These are some of my customers. We do podcasts, we do content development, we come to conferences and speak on stage and wear t-shirts. I'm here today on behalf of Humio, but if you have questions about any of these companies, please feel free to grab me in the hallway and ask. I'm happy to talk about all the people that I work for and work with. A little about me. So I come from Buffalo, New York. How many people have been to Buffalo, New York? Oh, wow. Okay, so you've had chicken wings. Awesome. So I don't have to go through that whole spiel. But it's a nice small town. We have a great tech community there, although no one seems to know that. We just did our first DevOps Days Buffalo a couple weeks ago, and it was awesome. People had a good time. Beyond being a technologist and a speaker, I've been playing in bands. I've been a musician since I was about 6 years old. I love doing karaoke, so if anybody knows of a good Scottish karaoke bar, please let me know. I was also a hockey coach for many years. This is my son in his second to last year before he retired. That's another whole story. And there's a picture there of my daughter, who at 11 years old keynoted the largest RubyConf in the world. So if you think you can't speak, if an 11-year-old can do it, you can probably do it too. But that's me. But what this talk is really about is Professor Alan Turing. This is Alan Turing. This is not Alan Turing. If you've seen the movie, it's a great movie. The Imitation Game is a brilliant movie, and it touches on a lot of the things that Alan Turing did in a very brief and almost perfunctory way. But this is a very Hollywoodized idea of what Alan Turing was like. Let's talk about the actual Alan Turing. Let's focus on him. He was a child prodigy, known by many as the father of modern computer science. He was a brilliant mathematician. He concerned himself with breaking through the concepts that we had of data in the raw. So when I say data in the raw, I'm going to use the words data and information not in two different ways. Data is just a raw thing. It's not information. It's not informative. It's basically just numbers. He understood that. He wanted to translate that into something usable. So while this is just like one of his many accomplishments, he did so many things. This is what we're going to be focusing on for the talk. So he was of a mind that you could use machines to actually take data and turn it into useful information. He knew that the human mind was capable of doing this. This is what we do every day. We take in data, we look around, we observe our world, and we analyze that with our brains, and we come up with information to inform us on how we behave and how we do things. He knew that that was something that people could do, but he also had a feeling that machines could do it a hell of a lot faster. But we have limitations. We have issues that we have to deal with. He was dealing with this in the early 1940s. So obviously he did not have like a MacBook or Hadoop cluster. He didn't have anything to work with. He just had the basic mechanics of what a computer might be. Before we get too far into it, what we're dealing with here in Turing's case is cryptography. Before the concept of big data and anything we even conceive of as computerized data, we had cryptographers on both sides of World War II. Okay, if you've seen the movie, you kind of know what Alan Turing was doing. His job was to take coded information from the Germans and translate into useful information for the British military. Seems kind of straightforward, right? Like, how hard could that really be? So there was this machine. This machine was called the Enigma. For those of you old enough to remember what a typewriter looks like, the keyboard kind of looks like a typewriter. And what you would do is with those 4 dials at the top, you would do your setting for the day. That setting would then determine which letters correspond with which other letters, and you would type out the message. The lights would light up on the side of the board there, and someone would sit there literally dictating exactly what you said. Then they would send out the message. Now, this doesn't look like an extremely complicated piece of machinery, does it? However, I'm here to tell you, it's still difficult to break the cryptography of World War II. To add to that, there's this great URL if you want to copy it down called enigmaathome.net. If you were to use modern computers to do what Turing did in 1940s with mechanical machines, you would still have a hard time. It's not easy. And then we're not talking like, 128-bit encryption. This is just basic cryptography. This is basically taking letters and turning them into other letters. However, the interpolation, because it changes every 24 hours, is extremely difficult, still to this day. After the war, and for those of you who didn't watch the movie, let me fill you in. So Turing figured out how to do this, and it was accurate how he figured out how to do this in the movie. They discovered that every message ended with the same epithet of, praising the leader of the Germans. I'm not going to say what the message was. We all know what the message was. But because of that, you had several letters that were repeating, and they were repeating in every single message. By establishing that as the base to break the cryptography, he was able to actually see what was going on. So the war ended. We won. Yay. Everybody's happy. But people were saying, well, he did some really interesting things. Where can we start applying these? People were starting to build machines that were replicas or copies of what he was doing. And one of the places was considered at the time a paramilitary organization who decided that maybe it would be really cool if those of us who were in America left and went to the moon. So they started looking at the things he was doing, this collection of data, figuring out how we could actually make a machine that would collect enough data, give us enough information that we could launch a rocket and go to the moon. How many people know the woman in this picture? Her name is Margaret Hamilton. I'm glad a lot of people raised their hands. Margaret was kind of awesome. She was the leader of a team who actually wrote the code for the Apollo and Gemini missions. Now keep in mind that these machines that were launching people into space, super safe, had about the computing power of 1/200th of the phone that's in your pocket. It was basically mechanics, it was buttons, you were hoping for the best. Many people didn't make it, unfortunately, and that wasn't just true in the US, it was also true in the Soviet Union at the time. We were just kind of making it up as we went along, kind of based on Turing's model. Like, we don't really have any data on how to go to the moon, but we'll just piece it together and figure it out. Now, if you know who Margaret Hamilton is, that's cool. How many of you know how tall Margaret Hamilton is? Margaret Hamilton is about 5'6", or about 168 centimeters. That is the code that was written for the first Apollo missions. That's just the code. That's not even the data they collected. But they used the techniques that Turing had to say, okay, we can start speaking to machines and making them do things so that we can do crazy things like going to the moon. Which, just on a side note, is kind of amazing because, when they talk about in the US, like, we're going to go back to the moon, why is it hard? They did this in, 1960. They figured it out in 1960. We have much more computing power. How can we not just, slap something together and go to the moon tomorrow? But maybe by 2025. Anyway, so things changed at NASA. It was formerly a paramilitary organization, and it became a space agency and aeronautics administration, which is really cool and sounds awesome, and they make great t-shirts. But things were moving really fast. So Margaret Hamilton was doing this in the 60s. In the 70s, they said, we need an orbiter. We need the space shuttle. Things moved so fast, and this is the 70s. A lot of people are like, oh, the 80s, like when Challenger had its incident. Yeah, but the space shuttle was actually developed in the early 70s, built in the mid-70s, launched in the mid to late 70s. It was a brilliant piece of machinery in comparison to those early rockets, which were basically some steel strapped to a missile, hoping for the best. And I know that there were complications later, but in the beginning, the space shuttle was one of the most amazing pieces of technology there was. There was just one problem with this rapid development cycle. One small caveat. By the time the space shuttle came around in the 70s, so we're talking like less than 2 decades between Margaret Hamilton and the space shuttle launching, we no longer had the capability to look at the data that was in those original Gemini and Apollo missions. It was kept on old tapes. Things were already moving to disk. Things were changing so rapidly that the data we collected was no longer manageable. You could not analyze the information that we had. It sits in vaults. Most of it is probably degraded at this point in time. And that's why it's so important that we go to the moon again, because do we have the information? We don't know. So of course, NASA in space is awesome. We all love space. It's, it's part of the reason why I got into technology, because I thought I'd be an astronaut and I wasn't. Just long list of things that I didn't become when I grew up. But it was so amazing that we could do this. So of course, who are the first people to say, okay, so this computerized data thing is really working. How do we get it? So business. The folks over at this little blue company that was basically known for making cash registers and a few other less pleasant things during World War II, realized that they could use data and information about their customers. They could analyze it and figure out how to get better customers. For those of you who aren't getting my vague reference, that was IBM. They were one of the first groups of large companies to say, we can use computerized data and manipulate it in order to have better sales, to better understand our customers, and therefore to better use it. Now, this wasn't data the way that we look at data. This was data that led to things like spreadsheets and other information. Microsoft Access, which for those of you who don't know is still the largest used database abstraction in the world. Let that scare you. So the idea was they wanted to follow the trail of money, so to speak. The companies began to use servers and mainframes. These concepts are all not new. This is still in the 70s. NASA's busy building Space Shuttle, and IBM's busy building, the first ever mainframes, along with the people at Cray and everything that was going on at that time. So we're not even to the point where people are using personal computers. They're logging into terminals and looking at information, and spreadsheets were a brand new thing. They were called digital ledgers at the time. And being able to look at that and figure out what was going on. They had the data, and they could look at it in a whole new way. Suddenly, information became a commodity. But we hadn't yet begun to look at the data of the machines themselves. So it would be very foolish and dismissive to say that a lot of this data that was lost at the time was due to short-sightedness. At the time, the idea was to collect as much data as you possibly can. Get all the data. And we're not talking about Google or Facebook, who are definitely getting all the data, just FYI for using those platforms. Sorry, Dave. But there was a cost to having so many tons of data and absolutely no way to process it. There's absolutely no way to look at this massive amount of data, whether you were NASA or IBM or any of the other companies coming along. You just had data. Now, I'm going to reiterate this again. Data is not information. It's not the same thing. So these people are all worried about, what does this information mean? What does this data mean? How can we manipulate it? We need to break it down. We need to analyze data in the raw in order to extract useful information. Enter big data. So capital letters, capital B, capital D, big data. It's kind of still a huge buzzword in the industry. Everywhere I go, I talk to people and we have big data problems. We have big data problems. I'm like, are you talking capital B, capital D, big data problems? And they're like, yeah, we think so. Okay, so that's usually where you have to break it down. You have to understand, what does big data actually mean? And it's broken down pretty simply with the 4 V's. Volume, variety, velocity, and veracity. So this is what they call them. This is what makes sense. This is kind of your checklist to see if you actually have big data issues, and we'll go over what each one means. First is volume. So for those of you who've been to Buffalo, Lake Erie? Huh? Nice. Yeah, that's where I live. My house is somewhere there-ish. Didn't show up on the map. I don't have a big house. But volume is the easiest one to understand and explain. Volume means a lot. But a lot of volume when it comes to data is kind of a matter of perspective. If I'm running an application that's a simple, straightforward application, let's say it just collects data from people when they post things on Twitter. You're using the Twitter API and you're just kind of collecting counts to see how often they tweet. The Twitter API is pretty widely used, but nonetheless, there's a lot of people on Twitter. But if you're just looking to capture maybe your customers to see when they're tweeting about you, it's probably not a ton of data, maybe 40 gigs of data a day. Does that seem like a large volume of data? What if it was 400 gigs? What if it was 4 petabytes? At what point do you decide that the volume is so much that you actually have a big data problem? So let's look at this through the eyes of Alan Turing. Did he have a big data problem? Did he have a volume problem? It doesn't seem that way at first because you say, well, how many messages can you possibly have in a day? Okay, so think about this. And I'm not asking you to take out your phones, but think about your phones. How many emails do you receive on a daily basis? How many texts? How many calls? How many responses on Twitter or Facebook or Instagram or Snapchat or whatever the kids are using these days? How many TikTok videos do you comment on? How many different forms of communication do you have, and how often do you use it? Just consider each one a message. And think about the volume that he had. So he was dealing with military data, which is still a large amount of communication every single day. We can definitely say that Alan Turing had a volume problem. Second part is variety. And this isn't as easy to pinpoint as volume. Volume is pretty straightforward, pretty clear. In the practical sense, variety is tough. What sometimes seems like diverse data is not always the case. Are you collecting, for authentication, email, first name, last name, password? That doesn't seem like a great variety of data. Add to that you have an e-commerce site and you're actually collecting previous purchases, method of purchase, credit card used, hopefully you're encrypting that in some way, preferences, how often you look at things. So this is kind of like your Amazon model. You know, they actually analyze every single thing so they can say, listen, you looked at a motor scooter one time because you wanted to see if Amazon delivered motor scooters to your house? They do. And now you're going to get an email once a week about how the motor scooters are on sale, even though you never had any intention of buying one. You were just curious about the shipping process. They have a variety. I can tell you, Amazon definitely has a variety of data on me, and probably a few questions somewhere along the line. You know, especially if you, we won't get into that. Anyway, so how do you figure out how many of those bits and bobs actually contribute to having a variety of data? I can tell you that most people do not, most applications do not collect a variety of data. Establishing that is what helps determine whether you have that second step towards big data. Again, Turing kind of has an issue here. People say, well, he was collecting military data. Yeah, but what is military data? Sure, troop movements, that's important. Shipping lanes, because there are a lot of, naval battles going on and submarines and stuff like that. So they needed to know shipping lanes because theoretically no one wanted to bomb like, a cargo ship. They wanted to focus on military targets. Air traffic control information. Day-to-day minutia. Where was Hitler going to be? They were communicating all this stuff because they kind of had this bravado that our stuff's encrypted. There's no way in hell anyone's going to break it. So we can say whatever we want. So I would say that he did have a large variety of data. Some of it was important, some of it was not. That kind of gets into our next step, veracity. So for those of you who have coded for a long time, veracity could have been replaced with truthiness, but saying the 3 V's and the 1 T didn't make sense, so they're like, all right, let's go Latin, we'll go veracity. So veracity is about the truth of your data. This is kind of where your personal value comes in. And I'll give you a perfect example. Not so long ago, I was working at a company, a platform as a service. We provided a way to get onto AWS with one click of a button. That's really cool, but whatever. We realized that at some point in time, someone who called themselves Mary Poppins had registered with the Very Nearly Perfect company. And we learned shortly after that, our security team, that Mary Poppins was a Bitcoin miner, like mining Bitcoin using AWS instances, because we had this free tier that you could use for 30 days, and they would use it for 29.75 days. Because we didn't have a great security team at the time. We're just kind of putting things together. Now, if we based our business's decisions on what Mary Poppins' company was doing, that would be very foolish. This was not true data. This was not how a majority of people used the platform. This was an anomaly. So that's how you kind of determine whether the data you're looking at is true or not. Now, with Turing, he had to figure out if what he was seeing was true or not. However, again, this is where the kind of German bravado comes in. There was no way the enigma could fail. There was no way anyone would ever figure out what they were saying. Therefore, say whatever you want. Make sure it's true and accurate because the troops have to get this information. Oh, and I forgot to mention, all this was going out over telegraph, so that's an even extra level of encryption. I have a whole other talk about the telegraph and the Pony Express, but that's another time. So did he have to worry about whether the information he was looking at is true? Not really. He knew it was true. Why would they not send important information or correct information over the line when they knew no one could read it? So it wasn't a concern, but it was veracity. It was true data. Finally, we have velocity. And I know in agile circles you see a lot of things about velocity and sprints and things like that. Not that velocity. This is about how fast you take data in. Velocity sometimes is also determined by your application speed, your performance, your ability to have site uptime and things like that. Raw data isn't always like the veracity you're looking for, but it does, even the not true data that comes in increases your velocity. When we look at the amount of data we're bringing in, we have to worry about whether or not we are bringing in valuable data. So we try to trim this down. However, your velocity will grow as your number of users grows over time, and you will be bringing in information. Like the two gentlemen I was talking to earlier who have a customer that has a table with 2 billion lines in it. 2 billion lines. I have a lot of questions about that. But they definitely have a velocity issue if they're bringing in that much information on a regular basis. Again, with Turing, by the way, he was an avid runner. Loved to run, compete. The idea that the Germans had no consequences means they could send messages all damn day. They didn't care. They were like, we're not worried about this. We're not worried about, not keeping up. Send every message you want because no one's going to figure it out. So he had extreme velocity. Add to his velocity the fact that those settings changed every 24 hours. Again, something the movie got right. They had 20 hours each day to figure out how to break the code. And without a machine, it was impossible. So those are the 4 Vs. Unfortunately, a lot of people don't understand this, and they have no concept of what's going on. They just think that they have a lot of data, which again is a perspective thing, and they say we have big data problems. Lots of data is not big data. You have to have all 4 parts of this pie to have big data issues. We add to that with a few complications. For example, part of the thing that we need to consider is how we bring all this data in. A while ago, there was a big movement towards NoSQL. There's a lot of solutions out there like MongoDB and InfluxDB, CrateDB, like a few of these different things that are basically built for big data. The idea is like if you have a simple application that's running with Postgres or MySQL and you're fine, you probably don't have a big data issue and you probably don't need those solutions. But NoSQL solutions are for when you have gigantic data problems and you have to look at them. So that's important. NoSQL definitely comes into play here. At the same time, there's a huge link that needs to happen between big data analytics. It's great that we have all this data. It's all very important. And this is where the DevOps side of things comes in, because data doesn't matter if we can't analyze it, if we can't look at it. Luckily, there's a lot of modern solutions for this. With the advent of big data and the push for more people using the complex applications we're building every day and the growing complexity of these applications, that more things are needed than ever before to process the information. We need to find ways of actually looking at information, not looking at data. Now, we're lucky. There's lots of things that are built. This is the pitch part. Humio builds a wonderful logging and monitoring solution that will bring in your data, give you information. It checks your infrastructure and your application monitoring, and that's great. There's also other solutions. Some are open source. Some are paid for. Some are really easy to set up. Some are not. It depends on what your organization needs. But the point is, if you have data, if you are bringing in information, if you have an infrastructure that is not one box sitting alone in a closet, please tell me you do not have one box sitting alone in a closet for production. Please tell me that. If you have one box sitting alone in production in a closet, you don't have big data problems. You have other problems. But whether you're using the cloud or using like bare metal, it doesn't really matter. You have so much information about infrastructure and application that you need a way to process that data. And cool, like I love it when my slides just double up. Oh, cool, this one's actually animated. That's awesome. But one thing that I do want to say about like the modern application monitoring, infrastructure monitoring solutions is pay attention to how they work. Some are flash in the pan. I've used several monitoring applications that it's like, cool, this is awesome, I love it. And then a week later, I'm like, oh, the company's closed because this actually doesn't work, and I was looking at bullshit all day. Apparently, I did not have an issue with CPU. I just had an issue with my monitoring solution. So keep that in mind. Test out. Find the things that work. Look for a little bit of longevity. You want to go with something that's a solid solution because what you're looking at is the information of what's running what you're doing. The first step in understanding the whole like analytics and data observability is getting a brief understanding of business intelligence. I know no one wants to hear about this part, but business intelligence is actually important, and it's kind of ingrained in what we do. The interesting thing that I find about business intelligence is that in reality, what we're seeing is developers and operators, systems administrators, need to know more about business intelligence than ever before. And I think this is great. And this is why. Like, because a lot of people are like, what? Why is this great? We don't care about business. We care about code. We care about infrastructure. But understanding business intelligence actually starts to put the science back into computer science. And that is like, when it comes to DevOps, that's the overarching part that we're all interested in. So understanding business intelligence helps you to understand how you can analyze the information that you have, how to build on the information you have, not just collect data and sit there and say, well, yeah, we have 140 users. What does that mean? That's just a number. How do you work with this information? How do you analyze it? Now, the key thing here is that it's a cycle. Everything is a cycle. You gather the data, you analyze it, you look at it, you take action. You take that action, the data changes. Now you have to analyze the new data, take action on that, figure out what's going on. It's an iterative process, just like anything else. One thing that I want to say is while there are easy solutions to big data and analytics, sometimes the answer is not always the most obvious thing. It's not the elephant in the room. I love Hadoop. Hadoop is awesome. However, you don't always need it. I worked at several companies who were like, oh, we're going to build a Hadoop cluster. I'm like, we're a startup that's been alive for 3 months. We have 7 customers. what the hell do we need a Hadoop cluster for? Not saying Hadoop is not a good solution. When you have big data, Hadoop is often exactly what you want. And it's open source, and it's easy to use. But you don't always need it. Find your need first. The first data you need to look at is what you're doing, what you want to do, and figure that out. Then you have information that you can act on when it comes to looking at the data of your customers and your users. Once you figure out what you're pulling in, you need to figure out what it all means. We start to look at things like, data science, which is another great buzzword. You have these preconceived notions when you build something. And I was talking about this a little with a few people yesterday. When we code something, we kind of have an idea of how it's going to be used in our mind. However, until it hits QA and the real world, we have no idea what people are going to do with it. Remember that Mary Poppins example I gave earlier? This is a perfect, we never had any concept that anyone was going to spin up a bunch of Amazon instances specifically to Bitcoin mine. But it happened, and we had to react. We had to take that data, turn it into information, act on that information. Luckily, we had a couple data scientists who were like, this is exactly what's going on. And if you're wondering what a lot of this has to do with DevOps, it comes under the heading of observability. Observability is kind of the biggest part of the DevOps cycle because you can't really do anything unless you've observed your system and understand what's going on and when. Like, yeah, maybe when you're actually writing the code, you're not observing your system so much because you're creating your system. And maybe when you're testing and releasing, it's a little less important. But when you deploy, when it's operating out in the world, when you're monitoring your system, it's key. You have to be able to look into things and gain insights from them. One of the things that we see a lot is this whole idea of cognitive insights, which is taking the data, analyzing it, and acting upon it. And part of this plays into some of the bigger buzzwords that are in the industry today. Machine learning and AI, and now this is officially a tech talk because I said those things. Blockchain. But seriously, like a lot of these things are changing the way, if you can teach a machine to understand when things are going to fall over, they understand that if A happens and B is about to happen, C will bring your system down. Let's make a change right away. Let's alert. Let's send out a pager duty alert. And if you can teach a machine to do this, you actually save hours. You automate your system, and it's a little bit easier. And a lot of these monitoring solutions have that. AI is also great. It's super well advertised. It's probably the greatest buzzword in the market today. Most of the AI advertisements you see are complete bullshit. Writing an algorithm behind your thing is not AI. I'm just going to come out and say it. Sorry if I've offended anyone. Please report me on the code of conduct. Just saying that you have AI because you wrote an algorithm on the back end does not mean you have an intelligent way to analyze your data. It's not the same thing. So Turing developed, this is kind of an aside, but Turing developed a Turing test, and this is how AI is actually supposed to work. This is the gold standard. If you can write something into a computer and that program, that information is used in a way that when someone interacts with it, they can't tell the difference between a computer and a human being, then you've successfully created an artificial intelligence. Can anyone tell me they've interacted with a proper artificial intelligence? And I swear to God, if anyone says Siri or Hey Google, I will start not giving out high fives. I will retract high fives. But this is the idea. Like, it's awesome. But it's all about the data and the information. And this is kind of where it works. Data is just a collection of potential information. It's your basis. You then process that, analyze it. It becomes actual information. Then you use your wisdom and knowledge to take action on it. Knowledge, yes. Wisdom, depends on the company. But this is the easy way we have of understanding how this all flows together. Big data is kind of a big deal. You probably can't see most of what's on this slide. But these are companies that are involved in the processing or manipulation of big data. When I say manipulation, I mean that in a positive way. You know, taking the information, culling it, getting out of the stuff that you don't need, giving you the information that you can actually act upon. There is almost every major company you've ever heard of. This is from 2017, which was the last time they did a survey about it. So some of the companies that are actually on here are not companies anymore, like Jawbone, which I thought was awesome, but wasn't. But that's kind of the whole thing. You bring this information in, you have data scientists that manipulate it, look at it, analyze it, and it's awesome. From the time of Turing until now, and like think about it, this isn't even 100 years. This is, at this point, like 80 years-ish, almost. We've gone from having a mechanical machine to having proper digital computers taking in information, taking in data, manipulating and giving back to us in microsecond time, which is awesome. Yet, we still have trouble breaking the Enigma codes. So think about that. So here's kind of the whole shebang. We put it all together. We look at the work of Turing from the perspective of modern big data, And on a larger level, we look at how things progressed from analyzing military data to the data of business to the information on the machines that we use today. And we made it all happen, and that's awesome. But at the same time, here's the bad news. I can't tell you what the right techniques are. I can't tell you what the right monitoring solution is. I can't tell you how to properly use observability. I can't even tell you how DevOps will properly work in your organization because it's all about perspective. What you do in your organization is unique to the people that you work with, unique to the people who created it, and unique to the way that things are getting done there. So what you have to do, this is the homework assignment side, is you have to figure out what works for you. Maybe you need a Hadoop cluster. Maybe you need something like Humio, just monitor your infrastructure. Maybe you need these things, and maybe you don't. But in order to figure that out, I hope I've given you enough information to decide what works and what doesn't. We can't always predict what's coming next. I was talking with someone earlier about, 10 years ago, none of us had cell phones that do the things that we do. Yet we have literal rocket power, literal space shuttle power sitting in our pockets right now. And that's amazing. But we can't guarantee that there's no gotchas. We can't guarantee that things won't come out like, maybe an OS on a phone that automatically drains your battery if you don't buy the new phone. Those are things that we never have any idea of what to expect. We're kind of working on a shaky foundation, and the fact that we've moved so fast, we didn't have anything solid. So in conclusion, Alan Turing did amazing things. He built the way we look at things in modern computing, and it's kind of crappy because he really got the shaft. Based on his lifestyle, literally the government killed him. Literally. They forgot about all the wonderful things. They forgot about the fact that he saved millions of lives with his information-saving technology. They forgot about that, and they worried about what was going on over here. And that's kind of the main point. Use the information you have to forget about what's going on over here. Accept people for the way they are, and deal with the information we're dealing with to build our applications and have modern and great infrastructures. And the best way to do that is to put things together in the way that makes sense to you. So with that, thank you very much. And I'll take questions in the hallway when you're around. Thanks.